Hi. So what we're going to do today are two things. First, we're going to make a quick review of Lagrange multiplier method that we learned during mathematics. And then we're going to put an interpretation on the Lagrange multiplier, something that we haven't done before. However, let's start from the beginning. So we've got a typical problem. So z is a function of x and y. Now, our task is to either find maximum or minimum of this function. However, we have some restriction. And restriction says that some function of x and y is equal to some c. So, how do we approach this problem? So, what we were doing before is we were creating Lagrange function. So, we made capital Z, and this capital Z was f of xy. Now, we were adding to this zero, right? And we said that this zero can have various different forms, right? In our case, what we need to do is to take into consideration the restriction that we imposed on x and y. So, what we can do over here is solve that c minus g xy is equal to 0, right? Now we can use this information that when this restriction holds, this difference is identically equal to 0. And we can substitute this for the 0 over here. However, we remember again another fact. The second fact is that if this is 0, then I can multiply it by any number that I want. And this is what I'm going to do. I'm going to multiply this 0 by lambda. Okay, so look, first let's put lambda up front, and then instead of 0, we're going to write this expression. Okay, and this was the problem that we were supposed to solve. And how were we doing it? First, of course, we needed to use first order condition based on first derivatives. So, what were we supposed to do here? First, we differentiate this equation with respect to lambda. We get c equals c minus g xy, and this, of course, needs to be equal to 0. Okay, then we need to differentiate this equation with respect to x. So we've got that this is fx, where this x here denotes derivative of function f with respect to x. Right? Then we will have minus lambda times gx, where gx is simply a derivative of function g with respect to x. And we equalize this with 0. And finally, we calculate the derivative with respect to variable y, where fy and gy are respective partial derivatives of function f and g with respect to y, and we equalize it with 0. Okay. And this created for us a system of 3 simultaneous equations that we could solve, of course, if we knew how the function f and g look like. And once we did that, we were able to find optimal values of x and y. Of course, for now, just candidates. Candidate for a maximum or a candidate for a minimum. However, let's remember a little bit about these equations. First one, right, is simply a repetition of the restriction we've got. So it introduces no new information in comparison with what we knew already. And the second two equations are the ones associated with derivatives. So here we are looking for the point with the zero slope. Here we are just making sure that the restriction holds. And look, if we solve these three equations, assuming that we know the specific forms of the functions, we should get three variables. This is a system of three simultaneous equations, so we must come with three variables. Of course, we're gonna get x, right, and y, because those are the variables that are variables of interest. Those are the ones we use for optimization. However, of course, in these calculations, we're going to get a third variable, right? This is a system of three simultaneous equations. And the third one is lambda, right? When we were learning about Lagrange multiplier method in mathematics, we got this lambda, but we said, maybe we're not going to interpret it at this moment because we do not have sufficient tools to deal with this particular problem. And actually that was the case. So we couldn't actually tell what lambda was. Now that we've used implicit function rule, we can apply it over here, and thanks to that, we will be able to get a proper interpretation on lambda. So how does it go? Well, first thing we need to do over here is to create a system of three simultaneous equations, right? That we've got. We need to take the system of three simultaneous equations that we've got over here, and rewrite it into a form that is in line with implicit function rule. So what we are trying to do over here is to assess if this system implies these three solutions. So we will have here three functions, f as a function of lambda, x, and y. And also we see that we here have one variable that is clearly exogenous, so we can take c to be put after semicolon, right? And this function is defined to be c minus g xy, and this should be identically equal to 0, right? And now we do the same thing for the other two equations. So we have three functions. F x1 is lambda g is equals to 0, and F3 lambda x y same. Okay, so now how are we checking if this system implies some specific functions? In our case, of course, this is going to be lambda. So some function lambda, where lambda is depends only on the value of the of c. So the number that is giving our constraint, and similar function for x, and similar function for y. Okay, so when is this system implying this one? Well, we know that in order to check it, all we need to do is to take the system and calculate its Jacobian, right? So let's do it. Okay, so what is our Jacobian going to be? Well, what we need to do when we calculate the Jacobian for some system, we need to take every equation and differentiate it with respect to every variable. However, look, our equations that we got to differentiate are derivatives already. Okay, maybe this will have some significance in the future. Okay, so we've got here three derivatives. Okay, and each of those derivatives need to be differentiated first with respect to lambda, then with respect to x, and then with respect to y. Okay, so let's do so. We have no lambda in the first equation, so we've got 0 over here. And then if we differentiate this equation with respect to x, we're going to get negative gx, and with respect to y, negative gy. Okay, then we differentiate the second equation first with respect to lambda. We get negative gx. Then we differentiate it with respect to x, so we get fxx. So we differentiated function f with respect to variable x twice, and then we've got minus lambda gx x. Okay, so now we need to differentiate this equation with respect to y. So look, now we're going to have derivatives of these functions here with respect to variable y. So we're going to have here fyx minus lambda gyx. Okay, and finally, we need to go to the last equation. We differentiate it first with respect to lambda, then with respect to x, and we get that this will be derivative of this function with respect to y differentiated with respect to x, and this function differentiate, so this derivative of function g with respect to y, now we differentiate it with respect to x, so we should get f and xy minus lambda g xy, and finally we differentiate this equation with respect to lambda with respect to y, so we get this is fyy minus lambda gyy. Okay, however, we should remember one more thing: Young's theorem. Young's theorem says that if I'm going to take a function and differentiate it with respect to x and then with respect to y, right, I will get exactly the same result if I would take this function, differentiate with respect to y, and then with respect to x. So we can argue that those two are identical and those two are identical, right? Because it's regardless of what function we use, we need to have the same result. So it's not going to be a big problem if I'm going to change this to xy and xy. Okay, and what are we noticing here? Look, we are noticing here that this is something that we already seen and already know very well, right? When we were learning about Lagrange multiplier, we learned that first we need to use first order condition. Then we need to use second order condition. And look here, actually it turns out that when we are trying to find this interpretation of lambda as a byproduct, we actually got our bordered Hessian. Right? This is simply the same bordered Hessian we used before. We clearly see that this determinant is symmetric, right? We see that those expressions are the same, those expressions are the same, those expressions are the same. So we see that the primary diagonal serves as a mirror, and this is exactly the bordered Hessian we were using. Okay, so what does this imply for us? Look, we remember that if Hessian is bigger than 0, bordered Hessian is bigger than 0, we have a maximum, right? Then we remember also that when bordered Hessian is lower than 0, then we have a minimum. Now, When Hessian is equal to 0, what we have is a problem. Well, because we usually don't know what is happening, right? It could be a maximum, it could be a minimum, or it could be nothing, right? We discussed the different cases where it might happen. However, we can be 100% sure that this is a maximum if this is positive, or minimum if border Hessian is negative. However, look, what we discussed right now are the conditions on Hessian. In case of Jacobian, those conditions are different. So, if Jacobian is different than 0, then we have that those three functions, that this system actually implies those three functions, right? If it's equal to 0, then this is not the case, right? So look, as it turns out, that if we have a maximum or a minimum, then actually Jacobian condition is met. And when we have a problematic case, this is also when Jacobian disappears and we cannot go on with the problem. So look, we clearly see that the interpretation of lambda that we're going to obtain here is directly associated with optimal value, right? Because this, whatever we're going to get from this moment on, works if and only if we either are at maximum or at minimum. If we are in some in-between problematic case, Jacobian disappears, and this is where we should probably stop our further reasoning. Okay, but we now can assume that we are only dealing with the cases we want. So either we are maximizing the function or we are minimizing the function. And if this is actually the case, then we can proceed. So look, what we have is that we have a system of three equations implied by this system, and we know now that that these equations that we see over here form an equilibrium. Okay, so let's rewrite them a little bit differently to signify that point. Okay. So we would have the first equation. Now we go C minus G x with asterisk y with asterisk to 0. F2, we would have f x as a function of x and y minus lambda with asterisk gx as a function of x and y. And then number 3, fy minus lambda g y x. Okay, so look, what we are interested now is to assess what is the impact of change in our one exogenous variable c on everything else, and ultimately on the big Z, right? Okay, so knowing what we know, right? We know we can find these optimal values of x and y. We know that this is either maximum or minimum because Jacobian is different than 0, as well as lambda, right? But what is a lambda? We will get it, right? So knowing this, I can solve this system, right? And I could simply take all these equations, all these solutions, and put them in formula for z, right? Why not? In this case, I would obtain optimal value of z, right? So this would be f So I'm just simply substituting all the optimal values as they are into the equation. And look, what do we need to do right now? Well, we are interested in what is going to happen to z, optimal z, when c changes. So we need to calculate derivative, right? However, remember that in this case, c is a function, and c impacts three different functions, right? It impacts optimal value of y, it impacts optimal value of x, as well as it impacts optimal value of lambda, right? So we need to get every possible channel of influence over here out in the open. And if we are doing this, this means that we need to calculate total derivative. Okay, so let's do it over here. So look, we need to differentiate every expression over here with respect to c, keeping in mind those are also functions of c. So look, first, c can influence x, right? And then x will influence z, right? So we will have here f of x, right? So derivative of f with respect to x, of course, evaluated at optimum, times changing optimal x due to c. Then we need to do the same thing with respect to y, right? Because c also influences y. So we get that this is fy times dy dc. Okay, here we need to use the product rule. Why do we need to use the product rule? Because here we have multiplication of two expressions. It's going to be easier if we will. Okay, so first let's assume that we are only differentiating, that we differentiate only the first expression, we leave the second expression alone, right? So we would get this expression, so c minus g out of x and optimal times y, and times derivative of lambda with respect to c. And finally, in the last expression, we are assuming that this stays the same, right? And we differentiate this expression. And look, what do we get? If I differentiate this with respect to c, right, it's just 1. Then minus derivative of g with respect to x times derivative of x with respect to c. Similarly as over here, so we will have gx dx dc, and similarly for y, so gy dy dc. Okay, and look, what we can notice over here, that some expressions can be put together. For example, here we have expression dx dc, and here we have expression dx dc. Why not put those expressions together, right? So we would have here f of x minus lambda times gx multiplied by dx dc. Okay, then similarly, you can notice that we have two expressions with dy dc. Okay, why do not we put them together? Okay, so we will have plus fy minus lambda gy times dy dc. Okay, and finally, the last expression that we've got over here, right? It doesn't need to, it doesn't need any changes, right? Sorry, g x y. And look, what we are left with is only one more expression. One, right? From this parenthesis that we haven't actually used. So now I'm multiplying 1 times lambda and, I'm sorry. So I'm multiplying 1 times lambda and I'm getting this result. And okay, what you might say over here is that it's really complicated. How can we read anything into it? However, look, what we know is that this is the optimal value of z. So this is how much z would be if x and y would be chosen in such a way to maximize it and still for this condition to be binding. Okay, so how can we use this knowledge? Well, let's look at it a little bit more thoroughly. First, we can notice that this expression in equilibrium should be equal to 0. But look, this expression is exactly the same as this expression, which means that this is 0. Then, from the third equation, we get that this expression minus this expression should be equal to 0, which means that this is equal to 0, and another expression out of here just gone. Then we move to the next expression that we've got over here. And look, this is nothing more than our 0, our restriction, right? We need to know that this restriction is binding, so C is actually equal to this. So again, we get 0. And from here, we are actually getting a proper interpretation of lambda, which is the only term that stays. Okay, so in other words, we get that dz dc is equal to lambda. And look, this is the proper interpretation of Lagrange multiplier. Lagrange multiplier, lambda, is telling you by how much will optimal value of z changes when c is increasing by some very small amount. So look, it is giving us a very, very nice tool to interpret, because we will know what happens to function z if the binding condition is relaxed slightly. And look, this is extremely important, because if we have some restrictions on our profits, that this will tell us how relaxing those restrictions will influence the profit of our company. This could be made as an argument: should the company invest more in productive capacities or not? There are plenty of application of it, especially in statistics. You will find that a lot of tests is based on Lagrange multiplier, the same one that we use over here. However, we are going to focus on a very specific economic interpretation of Lagrange multiplier, because Lagrange multiplier is marginal utility of money. However, why is it so? We're going to cover in next videos where we deal with the customer's choice model. However, let me just point you to a very important distinction. Look, someone could say that all we did over here was very unnecessary work. Why? Well, look, we spent so much time solving some complex derivatives and calculating some Jacobians. Why couldn't we just do this? Look at this equation. Do not assume, I do not have any information that x and y is a function of c, neither here. So what do I get from this? If I differentiate this equation with respect to c, I get lambda. Those results look extremely similar. There is, however, one difference, right? Here we have the asterisk. There's none, right? Would this suggest that the interpretation of this should be a little bit different? Well, look, of course, if this would be the function we are actually using and trying to differentiate, yeah, that would be the way to differentiate it, plain and simple. However, we are not interested here in what is just the derivative of this function. We are interested in how will optimal solution change when budget constraint is relaxed, when constraint is relaxed slightly. Look, what is like when we have the case that we're going to have with the customer utility, how much utility or happiness of the customer depends on is going to change when he's going to get one additional dollar, right? And if we do it, we cannot, we need to take into consideration the entire process of how customers will be spending this dollar on different goods. And this entire process is what is going over here, right? This is why we needed to find optimal solutions. And even though those results look very similar, we should remember that they represent a very different thing. Okay, so practical examples of Lagrange multiplier we're going to see once we're going to finish customer's choice theory. Take care and see you in the next video.